Finished filling out the right inputs for F or 15, and then 16 will be the lower order nibble will be a 0, so we'll start repeating the pattern for the right inputs. I'm going to go in and fill in the table for the address, and then the value that we're putting into BRAM, whether it gets written or not, we'll find out for sure as we go through these control words. We're also going to fill in these control bits, control words for control word 4, 3, 2, and 5 based upon the data path. And so, as you can see, and I'll go through and explain these as we go along. When you look at the data path, control word 5 is the read enable. That's going to enable reading, and it's going to be low right here on clock cycle 11 and 12, which are B and C. And as you look at the rising edge of the clock, that's for address 11, read address 11, and read address 12. And again, control word 4 is the write enable, and that's 1 bit to enable writing on the port. There's 2 ports, or 2 addresses, 4 and 5, for control word on the rising edge of the clock for 4 and 5 are both low for that waveform. And then which control words 3 down to 2 is which byte, high or low byte, is being written. If the most significant bit 3 is high, it'll write the high byte. Otherwise, if the lower byte bit is high, then it'll write the low byte. And if they're both high, it'll write both bytes. And since this is actually 16 bits, we actually have 2 bytes for the upper byte plus 2 bits. So we have actually 10 bits for the upper byte, and then 8 bits for the lower bytes. And those values are based upon wave 3 and 2. So 2 goes low here on address 6 and 7. So 6 and 7, the lower bits are 0, and then the next 2 clocks 8 and 9, the upper bits are low. So as we step through this and go line by line, the value that's going to get written and then read. So write enable, we're going to write these values into address 0. So we're adding these 4, they're going to be put into memory, and those values will get read on the output. So when we look at it in the waveform, we write address 1 or address 0 here, and on the next clock edge, that's when the read address is set to 0. So then after that clock edge, we're going to actually read that first value out, thus getting, it's going to let me run it, 2 AAA 0. That's the address that we're reading for that first one. The next address we're reading address 1. The value we're going to read out of that is 2 AAA1. 2 AAA3, and so on and so forth. Keep reading those values until we get to address 4, which we're not writing any values in there, and our value is reset to 0. So those, for these 2 addresses, 4 and 5, 4 being read right here and 5 being read right here, will both be 0. So 5 zeros. So 0x 0, 0, 0, 0, and 0x for that value. Then for 6 and 7, we're only writing the high nibbles. So for those, we should get only the top 10 bits. It's going to let me click in there. All right. For those bits, we're only going to get 2AA. That covers the upper 2 bits plus the 2 nibbles for AA. And that's what we're going to be reading out for those 2 clock cycles as well. 0x to AA 0, 0. All right, and then we're going to write the lower bits for the next 2 clock cycles, 4 clocks, address 8 and 9. So 8 gets written right here, and we're going to write the value, the lower nibble of that, which is A8, with 3 zeros. So 3 zeros, A8, and 0, 0, 0, A9. Right? And then we're going to read those same values because we'll read enable 0x 0, 0, 0, A8, and A9 for the 18 bits. The next one, on address 11, we should be writing that value in. 11 is B, or 10. 10, we're writing AA, all A's, right? So for the read value on that, since we're writing both bytes, we're going to read both bytes 0x to AAA. Next one, we're not going to read any value, so the value that's already on the line is going to stay on that line. So we're going to have the 0x to AAA on both of those next clock cycles. Since we're not reading a new value, whatever's on the line will stay on the line for those 3 clock cycles, and we can update our waveform to reflect that to AAA. So we got that value. The last one, or second to last one. So we got on line D, we're writing to AAAD. That value should get read out. To AAD, because that's what was written at address 14. And address 15. A D 0x 2 A, that's 14 E, and then 15 F 0x 2 AF. And again, for address 15, 0x 2 AE. That's for address 14. We're reading it here, and on that clock cycle, we read that value out. Again, that's the waveform. When you run this with Xilinx, if you run the simulation, you're going to get the same data out that we proposed in the waveform, because the control signals are being run in that data path. They're actually embedded in the data path. So as it's running the simulation, look at our waveform configuration file. You need to run that for 9 microseconds. 9 microseconds. Run, and notice we get the same values we talked about. All those control signals where we have zeros, because we're not writing values, we're writing the upper bytes, we're writing the lower bytes. Then we have read values stays on the line when we're not having that read value, and then AAD and AAEF. You can download the code for the data path and the test bench and the waveform configuration file and run this as well to see how that runs on your own machine. Make sure you understand how the reads and writes happen the reads happen after the writes and on at the same time, but on different addresses, right? So we offset the address by 1 in the example just so we know we're reading and writing at the same time. Okay. The other thing we're going to talk about is packages. We are going to use them in Lab 2 as a nice way to hide a lot of our component declarations. So basically we're going to take our components and instantiate them in it sort of as a header file for the HDL. So we instantiate it once and then we never have to declare it again. So we just add that package to our project pack file, and I'll give you an example in Lab 2, and all the component declarations are in one file, and so if we're using them multiple times, we don't have to update all declarations if we add one line to an instantiation. How do we create a package? So this is an example. If you click on this link for Lab 2 parts package, and this all it has in there, it's you're including the libraries, and then you create that package Lab 2 parts is, and then we have all our component declarations. So for Lab 2, we're going to have a flag register, an audio codec wrapper, a finite state machine, data path, and a video component. You can add in the other components that you had in your design to that parts kit. And it makes things all in one central location. So if I wanted to add, let's say you have multiple flag registers instantiated, if you wanted to just add one more port to that, you could just add it in one component declaration. And then in the top of your code, all you have to do is include the line use work, the workspace, lab2parts.all. Make sure you have that included in your project. Last thing we're going to talk about is a two-line handshake. In most cases, digital systems require data from an outside world in order to perform their tasks. Cases where digital systems, these systems operate on independent clocks, and being able to transfer data from one unit to the other gets a little complicated because there is no common clock. Unless you send the clock, sort of like we learned with the PS2 keyboard. It had its own clock to reliably transfer those bits of data over that serial connection. So, following scenario, we have a producer and a consumer. And over time, this shows over time, 1 through 5, doesn't matter the units, and volume is on the Y scale. So we have our producer, he's saying, starts here and says, hey, goes into a room, and he says, I got M&Ms, I have an M&Ms, and he keeps screaming that until the consumer who owns the M&Ms, finally at between time 2 and time 3, he says, takes those M&Ms and then says, starts screaming, I got those M&Ms, I got those M&Ms, until the producer hears that and stops screaming M&Ms. And then once he stops screaming M&Ms, then the consumer can stop screaming, I got the M&Ms, I got the M&Ms. And both are happy. And that is a timing diagram of the data transfer between that producer and the consumer over time. We can evolve this with a protocol, a two-line handshake, essentially. This is, regardless of who the producer or consumer is, we can use this two-line handshake to coordinate these request and acknowledge signals via one data line. So we use the request signal by the active agent to signal the readiness to perform some sort of data transfer. The acknowledge signal is used by the passive agent to acknowledge the data has been transferred. So request and acknowledge. And this is sort of a pseudo code algorithm that talks about it. So while request is equal to 0, do nothing but wait, right? This is just a while this is 0. Once it becomes 1, we register the data, latch the data in. The consumer will then acknowledge by sending out a 1 to the producer, telling them that they acknowledge that, and we wait until the producer drops the request signal low again to basically acknowledge the consumer's acknowledge, and then the consumer will drop the acknowledge signal. Similar to this signal, right? We have our request line and our acknowledge line. And that helps do the two-line handshake between them. This diagram basically demonstrates the data path and control for this system. So we have data path, we're registering that value. We have request coming from the external world, and acknowledge coming from the control signal. So this is like status words and control words for our control system, right? And all it's doing is going through several different states, just like the pseudocode here, right? Wait while request is 0. Once request is 1, we get that value, and it's going to register that value from the external world into the register. And wait here while request is 1, and once that drops, and then it goes to the next. And in so doing, the outputs to this control system are the acknowledge system to the external world, where it's acknowledging and then dropping that acknowledge signal, that two-line handshake. We're going to skip this exercise, but, well, let's do it. We can build a circuit to read in an 8-bit key using this two-line handshake. Circuit is a passive consumer. Circuit should search 18K by 18 RAM, counting the number of words that match the key, essentially. And this is just a generalized system. It's going to go through while request is 0, so it's starting out the same way as it was before. Request is 0. We check the data, see if it's equal to the key. We send out an acknowledgement. While request is 1, we wait, and then once that goes to low, we drop our acknowledge and set this match to equal to 0, and then we're going to go through and check from 0 to 8,191. We're going to read those values of RAM and see if the key matches our value in our register. And if they do, then we'll increment match plus 1. And that's about it. Again, with your homework, you should have